All right, so this is the intro to the sine function. So recall that in the previous task, we found Carlos's height at different positions on the Ferris wheel using right triangles as illustrated in the following diagram. So remember we said that the radius of the wheel was 25 feet, and we also said the center to the ground is 30 feet, so that was this distance from here to here. So Carlos has been carefully timing the rotation of the wheel and has observed that the Ferris wheel makes one complete rotation counterclockwise every 20 seconds. So that means one time to go all the way around the circle. So if I'm just draw another circle over here. So if we start here, all the way around is going to take us 20 seconds. And we're going, of course, counterclockwise, which would be this direction. So we want to figure then if 20 seconds is all the way around, and the question says how high will Carlos be 2 seconds after passing position A on the diagram, we first need to figure out how much 1 second is. So if 20 seconds is all around, we can complete this knowing that a full circle is 360 degrees. So 360 degrees divided by 20 seconds is equal to 18 degrees per second when you divide. So that tells us at 1 second we have 18 degrees. So if we add 18, 18, we get 36. So that 36 would be 2 seconds, which would be right here at B, because 18 degrees is half of 36, which would be about here. So that means that every 2 seconds we have are hitting these points on our wheel. So this is 1 second, 2 seconds, this would be 3 seconds, this is 4 seconds, etc. So how high will Carlos be 2 seconds after positioning or passing position A in the diagram? We can use our triangles like we did before to help. So we have our right triangle here. We're going to use our right triangle trig. So if we know that for our triangle, this angle is 36 degrees, and we know this is the radius, which is 25 feet. We want to figure out this height over here. So that's opposite, and we have the hypotenuse, which we know is sine. So that tells us that the sine of 36 degrees is equal to h over 25. So h is equal to 25 times the sine of 36 degrees. But then remember that we're trying to figure out the height from the ground. So that means we need to also add that 30 feet. So if we go ahead and plug this into our calculator, the first thing I would do is make sure my mode is in degree mode. So if I turn my calculator on, notice that it's in degrees. If it's not, just scroll down and hit enter on degree. So when I plug this in, we have 25 times the sine of 36 degrees plus that 30 feet from the ground. So that gives us 44.69 feet. So that is how high Carlos is going to be. So for question 2, it says calculate the height of the rider at each of the following times t, where t represents the number of seconds since the rider has passed position A in the diagram. Keep track of any patterns you notice in ways you calculate the height. As you calculate the height, plot the position on the diagram. So we have two different diagrams. So the other day we were making the height of the rider using right triangles and reference angles. So now we're going to look at it in terms of the angle of rotation. So we already talked about the fact that we know that 18 degrees per 1 second because it takes 20 seconds to get all the way around. So let's just go ahead and label that. So we know this would be 1 second here. This would be 2 seconds, 3, 4, 5, 6, 7, 8, 9, 10. And of course, all the way around would be 20. So we started there at 0 and 20. So that means with the first angle of rotation, that would be from here to here. So that first angle of rotation we know is 18 degrees. So we're going to use that, 18 degrees. And if we use our reference angles like we did before, again, we know that that would be this triangle right here, which again is still using the 18 degrees. We know that the radius is 25. So again, you're trying to solve for h and you're adding that 30 to your equation. So remember that for this triangle here, we have 18 degrees, h, and 25. So the sine of 18 degrees is equal to h over 25. So h is equal to 25 times the sine of 18 degrees, and then plus the 30 because we have to add from the ground, because from the ground to the center of the wheel we know is, again, 30. So that's where that comes from. And same thing for the angle of rotation. So we know this is also 18 degrees. So then when we get our calculators, we're going to go ahead and plug that in. So for this, we have 30 plus, and you can put the 30 on either side. It doesn't really matter. I'm just going to put it in front. So 30 plus 25 times the sine of 18. And we notice that gives us 37.73 feet off the ground. So now let's look at the next one. So the next one would be 2 seconds. So if we go 2 seconds, we know that's from here to here. So 18 plus 18 gives us 36 degrees. And that would be then this triangle right here. So now we're doing 36 degrees for the angle rotation and 36 degrees for the reference angle. Remember, we talked about reference angles before. Reference angles are the positive acute um, angle made with the terminal side and the shortest angular distance to the x-axis. So these are all acute in what we would consider the first quadrant. If we were to think about putting these on axes, this is quadrant 1, 2, 3, and 4. So they would be considered all acute in that first quadrant. So if we plug this into our calculator, I'm just going to hit enter. So change that 18 to 36, enter, and we get 44.69, which we knew from what we did on the first problem. So 44.69 feet. And now we're going to do the next rotation, which would be 3 seconds. So from here all the way to here, 36 degrees plus another 18 degrees gives us 54 degrees. So that means this is 54 degrees. And this would also be 54 degrees. So that would be this triangle right here. And so if we plug that into our calculator, same thing, we're just going to change the 36 to 54, and we get 50.23 feet above the ground. And now if we do the next one, that would be 4 seconds from here to here. Oops. So if we add another 18 degrees to 54, we get 72 degrees. So that would be, again, this triangle right here. So now we're using that angle from here to here as 72 degrees, which we did the other day on our Ferris wheel. So this number is going to look familiar. So if we plug in 72 degrees in our calculator, we get 53.78 feet. And now the next one, which is from here all the way to here, which would be another 18 degrees to the 72, which gives us 90 degrees. So 90 degrees. If we plug that in, we get 55 feet, which makes sense because we have 30 feet from the ground plus another 25 feet gives us the 55 feet for the maximum, because we know the radius from here to here is 25 plus the 30 from the ground. So that gives us 55 feet. So again, for that one, we can't really make a triangle. So for that one, we were just using the fact that we knew the radius of the wheel plus how high off the ground we are. So now let's go ahead and keep going on our circle. So this was all for the first quadrant. Now we're moving into quadrant 2. So if I keep moving on my circle, well, the angle of rotation then would be from, I'm going to use this color black again, from here all the way to here. So now we're doing 90 degrees plus another 18 degrees, which gives us 108 degrees. So that's the angle of rotation. However, we can't use the angle of rotation when we're talking about reference angles, because remember, reference angles have to be the positive acute angle made with the terminal side and the shortest angular distance to the x-axis. So we're going to use the fact that we have reference angles and the same triangles. So this triangle here is going to give us the same distance as this one here that we had, because notice it's using that same triangle, which we said was 72 degrees. So the reference angle that we're using is 72 degrees. So let's go ahead, and we already know 72 degrees. When we plug it in, we should get 53.78. So let's go ahead and just plug in with the 108 and see what happens. So if I plug in using my angle of rotation instead, notice that that still gives me 53.78. So if I use the angle of rotation or if I use the reference angles, I still get the same answer, 53.78. So let's go ahead and look at the next one. So if I keep going on my circle, then I'm going to add another 18 degrees to the 108, which gives me 126 degrees. And so if I'm doing 126 degrees, I'm using this triangle right here, which we said was the 54 degrees for the reference angle. So if I plug in on my calculator, 126, I know that should be the same as 53.23 because that was a reference angle of 54. So notice we get 50.23 again, because it's the same height as this point on our graph, just like these two are the same height. So that means for point E, which is after 8 seconds, you can see right here. So after 8 seconds, the angle of rotation, if we add another 18 degrees to that 126, we get 144 degrees. And that should be the same as the reference angle 36 degrees, because that's using this triangle right here. And you can even see that E and B are the same height on the wheel. So if we plug that in, we would get 44.69 feet. And we could keep on going. So the next angle rotation would be at 9 seconds. So at 9 seconds, I'm right here, which notice is the same as 1 second. So that is using this same triangle right here. So for the angle of rotation, we're going to add 144 plus another 18 degrees, which is 162 degrees. But the reference angle that we're using is 18 degrees. So if we were to plug this into calculator using the angle of rotation, we would end up with 37.73 feet. So now, of course, if we're going all the way around, A and F are the same height. And so for the angle of rotation, 162 plus 18 degrees would give us 180 degrees. And the reference angle doesn't make a triangle. So this one uses 90 because we're using this angle here. But if we're on the axes, we're going to use 0 because it doesn't make a triangle. And so for that, that gives us then a height of 30 feet, which makes sense because it's the center of the center of the wheel, which is from the ground up. They told us in the problem 30 feet. So that was for quadrant 2. So now we can continue to do this in quadrants 3 and quadrant 4. So I'm just going to keep adding to each of these values 18 degrees. So 180 plus 18 gives me 198 degrees, which again would be using this triangle, which is 18 degrees. And the one that would become after that, 198 plus another 18 degrees is 216. And so then the reference angle would be 36 degrees because we would be using this reference angle right here. And for the next one, 216 plus another 18 is 234 degrees. And the reference angle we're using is 54 degrees. And we're going to keep on going. So that would be this triangle here. And I just haven't done the angle of rotation because it's hard to draw all those pictures on here, but basically that one would be going all the way to 13 seconds from here all the way to here. That's an angle of rotation of 234 degrees, but again, the reference angle we're using is just this angle right here because it's the positive acute angle, which is 54 degrees. So then the next one after that would be adding another 18 degrees. So if we add another 18 degrees, we're going from the x-axis all the way around to here. So that would be, oops, sorry, right there, to the 14 seconds. So that gives us 234 degrees. No, that was the last one, 252 degrees. And the reference angle we're using would be for this triangle right here. So that angle is, of course, we know 72 degrees. So now notice the difference is in the first two quadrants, we are above the 30 degrees, but when we get to here, we are below the 30 degrees. So notice for the reference angle, I am now not adding the 30 degrees, but I'm subtracting the height, 30 minus the height, because whatever the h we find for each of these, this is the height, height, height. Now we're taking 30 minus that. But notice that for our angle of rotation, I didn't have to use the subtraction. I'm still just going to plug it in because the angle of rotation takes that into account. So if you watch, if we do 198 in here, notice we get to 22.27. And if we do 30 minus 25 times the sine of 18, notice we get 22.27 because again we're below, so you get the same thing. So the nice thing about the angle of rotation is that it takes into account what quadrant you are in, so you don't have to change your equation, which is why we like using the angle of rotation versus reference angles, but you can still find the solution using your reference angle. So this was 22.27, I think. Let me double check. So then if we were to do the next one and plug it into our calculators, we get 15.31 feet. And if we did the next one in our calculator, we would get 9.77 feet above the ground. And the next one, which is the 14 seconds, would give us 6.22, which remember is familiar from the other um, unit that we did the other day. So that would be the feet off the ground. So we have the 6.22 here. So I put the heights in just so you can see what's happening with the angle of rotation and the reference angles. The heights in quadrant 1 and 2 gave us the same thing. So that means in quadrant 3 and 4, we should get the same heights because it's below the 30. Of course, we have our next reference angle, which is at 15 seconds. So at 15 seconds, notice that our angle from here to here is 90 degrees to the x-axis. So we're using that 90 degrees. If we're on the x-axis, it's 0, but here it would be 90. So then for our 15 seconds, again, we're just going to add. So I'm going to pause the video for a second, just add in the angle of rotation for each of these. So I just added in the angle of rotation and the reference angles. So at 90 degrees, we know we're down here. So we know that the tallest part on the wheel it is 30 feet above ground and the radius is 25. So that without even plugging this into my calculator, I know that's going to be 5, but you could also plug it in just to double check, make sure you get that. And so the next one where is the 6.22. So that's this triangle right here with this reference angle. So 288 degrees would be from here going all the way around to here. So with that, that tells me that 288 degrees is this going to give the same answer as our reference angle, which was 72 when we subtract the 30, but here we just add it. So we know that should be 6.22. And the next one, when we go to 17 seconds, that would start here and go all the way around here. That would be 306 degrees. And our reference angle we know would be using, our reference triangle would be using this reference angle right here. And we know that should be 9.77. So if you double check by plugging in your calculator, you should get 9.77 feet off the ground. And so then the next one would be from here all the way around to 18, which would be 324 degrees. And the reference angle is using this, this triangle right here, which we know it should be 15.31 feet because it's the same height as G on the other side. So 15.31. When you plug in your calculator, you should get the same thing. And from here all the way around to 19 seconds, we know is 342 degrees, because again, we're just adding 18 degrees each time. And that's using, of course, this reference angle right here. So it should be 22.27 when you plug that into your calculator. And then, of course, we get to the last one, which would be all the way around our circle. So from start to finish, all the way around, we know is 360 degrees. And we know then that the reference angle we're using would just be on the x-axis, so 0 degrees. And we know that that height from the ground is 30 feet. So when we plug that in, we should get, oops, I should put degrees, we should put get 30 for our feet. If you don't, then just check how you plug it in and make sure you're in, again, degree mode. So that gives us all those values again. That's one way of doing it, using the angle of rotation versus using our reference angle. So if we look at this angle of rotation that we have here, what did we do each time? So we had y is equal to, we added the height from the ground, and the depending on which quadrant you're in, the calculator with the angle of rotation takes care of the positive and the negative of your height of your sine. So for this, even if we were to look at like just if I look at 25 sine of 288 degrees without the 30, so 25 sine 288, because notice it gives you a negative answer because what we're going to be talking about later is that sine is actually using the y coordinate from a point on your circle. So it actually takes into account that it's in quadrants 3 and 4 that the y value is negative. So that gives you the negative height instead of when you're doing the reference angle, it gives you the positive one. So that's why we don't have to worry about doing 30 minus like we do for the reference angle. So what are we doing each time? We have 25 because that was the radius times the sine of, and we took the 18 degrees times the time for each one, right? Because that's all we're doing is we're adding it. So 2 seconds, 18 times 2 is 36. 18 times 3 is 54. 18 times 4 gives you 72. 90, etc. So if I did 18 times 20, I would get 360 degrees. So for that, go ahead and see if you can do these last ones on your own. And you can then, when you're done, unpause the video and we can check your work. So I just did the first few, so 414 degrees, which is for would be for 23 seconds because all I did was 18 times 23 gives me 414. And again, it's 23 seconds. So if all the way around to here is 20 seconds, this would be 21, 22, 23. So I know that's going to be the same as 3 seconds, which is the 54, the blue triangle. So the 54 degrees for the reference angle. So that gives me 50.23. And then the next one, 504 degrees, is 28 seconds. So again, if I just keep counting on my circles, so that's 21, 22, 23, 24, 25, 26, 27, 28 is going to be the same as E, which is the green triangle, which is a reference angle of 36 degrees, which is why I used the green. So that tells us that's going to be the same height as E, which is 44.69. And again, you could plug it into your calculator to check. So 630 degrees is going to be the same as the 90 for the reference angle. So that would give us, in this case, 5 feet. Since you would be all the way down, so 28, 29, this is 30, 31, 32, 33, 34, 35 is all the way down here. So that's 5 feet off the ground. And then the next one uses the reference angle of 72. So if that's using that 72 degrees for the reference angle, and again, we are again below, same thing with here, we're below. So that tells me that for 36 seconds, we have 6.22 feet. And again, you guys can finish those last two on your own. So it says examine your calculations for the height of the rider during the first 5 seconds after passing position A. During this time, the angle of rotation was somewhere between 0 and 90 degrees. Write a general formula for finding the height during this time. So for this one, um, this is where we had the height is equal to, we added the 30 plus the radius, which is 25 times the sine of the angle that we had. And so that theta could be for the reference angle. If we did our height using our angle of rotation, it was 25 times the sine of 18t plus 30. So this would be for the reference angle, and well, this one's for the time in seconds. And so remember, this was the 25 is the radius for both equations. 30 is the height from the ground to the center, so we'll call this the midline. And of course, h stands for the height off the ground. And so this one was for the angle of rotation. So then how much you find the height of the rider in the other quadrants of the Ferris wheel when the angle of rotation is greater than 90 degrees. So what did we do? We looked for patterns. We also used reference angles. To help us. And we also used this equation up here with the angle of rotation. So based on the data you calculated in day 1 and day 2 notes, we're going to sketch a graph of the height of the rider on this Ferris wheel as a function of time elapsed since the rider has passed the position furthest to the right on the Ferris wheel. So we can consider this position as the rider's starting position at time t equals 0 seconds. So I'm going to put what I call the midline at 30 feet because that is from the starting position. And if we think about our Ferris wheel, so that is here where we're starting. So the midline is what we call the middle of our graph, and our graph is going to go up and down from the middle of this graph. So at 5 seconds, because the time, this is seconds here, and this is the height in feet. So the x-axis is the time in seconds. So at 5 seconds, if you go look back at your chart that we did up here, notice that we are at 55 feet. So at 5 seconds, we have 55 feet. And then at the next one, we'll do 10 seconds. So if you go back to your graph up here, that we had for the charts. So at 10 seconds, notice we are at 30 feet. So we're doing every point here. So we're going to do, this was 5 seconds, 10, 15, all around is 20. Because these give us what we call our key points on our graph, which we'll talk about in a second. So at 10 seconds, we're at 30. So we started here at 30. And then at 15 seconds, we're 5 feet on the ground because that's the lowest. And at 20 seconds, we're back to the starts. So this is what one time around our Ferris wheel looks like. So to get these points, these are what we call the key points on the graph. And to get them, you take the period and divide it into 4 equal points. I'm going to use KP for key points. So in this case, 20 divided by 4 gives us every 5 seconds. Why do we call them key points? Because they're the maximums and they're also where you hit your midline. So this is, again, is the midline, which is the center of the wheel, which was at 30 feet. And notice that the distance from here to here, or here to here, so from the midline to the maximum, because remember this is the maximum, which is at 55 feet, and the midline to the minimum, which is at 5 feet, is the same distance. So that is 25 feet, and that's what we call the amplitude, because our graph, notice, goes back and forth between this midline. So the amplitude is how high your graph is going to go. So for this, one wavelength, which is the same as a cycle, we also call the period. So the period of the graph equals 20 seconds, which is the horizontal distance to complete one time around the wheel. So if we wanted to complete another time around the wheel, 25 seconds, we would be back here at the maximum. And then at 30 seconds, we'd be back to the midline. Then we would be, because we'd be here, and then the next one would be 35 seconds, which would be at the minimum, and at 40 seconds, we would have gone around our Ferris wheel now twice. So if I did this, this would be a second time around our wheel. Whereas this was the first time around. So that's what a second wave would look like. So it says, for question number 6, how would your graph change if the radius of the wheel was larger or smaller? So if the radius changes, notice that's the amplitude. So that changes the amplitude, which is the height. So how high or low off the ground. So if it was a larger height, maybe something like this, and we could have a smaller height, maybe something like that. So that would be a larger radius, and this would be smaller. So if the height of the center of the wheel was greater or smaller, that would change the midline, which moves your graph up or down. So again, it would just change this line right here, moving it up or down. If the wheel rotates faster or slower, this changes the cycle or the period of the wave. So if we were to rotate faster, then your wave would complete faster. So instead of 20 seconds, we were to do it in 15 seconds, then you'd be going faster around the wheel. So for the next one, so that was for how the graph would change. So question 7 says, how does the equation of the rider's height change if, so now we're looking at the equation. So if we go back to the equation that we use, h of t is equal to a times the sine of bt plus d. So we're going to use that equation. So the radius of the wheel was larger or smaller. So that's your a value. So it changes um, the coefficient in front of the sine. So that a value. The height of the center of the wheel was greater or smaller. That changes, that's your d value. So it changes the constant. And the wheel rotates faster or slower. So that would be your b value. From our equation that we had, because remember we had y equals 25 times the sine of 18t plus 30. So that's all the different values I had. So this is just the general equation, and this is the one that we were using. So the next one, question 8, says, write the equation of the height of the rider for each of the following. Ferris wheel t seconds after the rider passes the furthest position. So why don't you guys do these on your own? And then you can check your work using the key. And that's it.